We're about to start talking about norms of matrices, but before we do that, let's review what a matrix really is and how it fits into linear algebra. Before you discuss matrices, you really should understand the concept of a linear transformation. What is a linear transformation? A linear transformation is a function, let's call it L, that maps a vector of size n into one of size m. And it has to have the following two properties. If you're given a scalar and two vectors, if you first scale a vector and then you transform it, you must get the same answer as if you first transform the vector and then scale it. And if you add the two vectors together first and then you transform the result, you must get the same answer you get if you first transform the vectors and then you add them. And it turns out that many functions of vectors actually have this property. Functions like rotating a vector, mirroring a vector, and various other functions. Linear algebra is the theory of how linear transformations act on linear combinations of vectors. And it turns out that you can represent linear transformations as matrices, and therefore the study of linear algebra becomes the study of matrices and vectors. And let me show you that link. How does it work? What are linear combinations of vectors? If we're given a bunch of vectors, k of them, v0 through vk minus 1, and we're given a bunch of scalars, k of them, chi0 through chi k minus 1, then a linear combination of these vectors using these scalars is given by chi0 times v0 plus chi1 times v1, and so forth. Right? Now, what if we apply the linear transformation L to this linear combination of vectors? Okay. It's not hard to see that by applying these rules over and over again, we get that we can apply the linear transformation to the individual vectors. And then take the linear transformation of those vectors using the same scalars, the same coefficients as were used to create the linear transformation of the vectors. Okay. In other words, just like you can scale first and then transform, or transform first and then scale, and add first and then transform, or transform first and then add, we can take the linear combination of the vectors first and then transform, or we can transform the individual vectors first and then take the linear combination. All right? And this turns out to be crucial. Why? Well, there is a special set of vectors in Cn that are our friends. We call them the standard basis vectors. What are they? E sub j is the vector of all zeros with a 1 in the entry indexed with j. Okay, so E0 is 1 with all zeros, E1 is 0, 1, and then all zeros, and so forth. Now, importantly, any vector x, if you expose its components, can be written as the linear combination of the standard basis vectors. That's pretty obvious. What now if we take this linear combination and plug it in? Okay, so if we change this, well, let's leave that alone. But what we can do is here we can say, let's plug in the standard basis vectors, the linear combination of the standard basis vectors, which means that we need to change this to n and that to n. So now we actually have n coefficients. Then we can first transform the standard basis vectors and then take the linear combination of the result. All right, now why is that so important? Well, notice that if we simply take our standard basis vectors and we compute what vector comes out, and then we throw away all of our knowledge about what that linear transformation is, we still have all of the information needed in order to evaluate L of x. This is just L of x. Okay? All information about the linear transformation is encoded in these vectors right here, which you get by transforming the standard basis vectors. What we can then do is take all of those vectors and make them the columns of a two-dimensional array. That two-dimensional array of numbers now encodes everything you need to know about L. All right? This here now we call the matrix associated with the linear transformation. And we can give it a name. We can call it A. Okay? Let's erase something. Let's make some room. We don't need this anymore. If we now want to evaluate L of x, we can instead utilize A and our knowledge about the coefficients of x, and we're going to write that as AX, and we're going to say that is a matrix times a vector multiplication. Okay? If we now expose the columns of A, because after all it represents this two-dimensional array of numbers, and we expose the coefficients, the components of x, then we see that matrix vector multiplication should be defined as the linear combination of the columns of matrix A. And that's the link between a linear transformation and a matrix and matrix vector multiplication.